All right, good. Is it still morning? Good morning, everyone. I'm happy to introduce Drew, Jordan, and Clint, and they're here to talk to you about their fixture design for shock testing of a Hellfire missile. I hope you enjoy it.
All right, thank you, Dr. Davis. So to give a little bit of overview of what this presentation will cover, we'll first go over the background of what a Hellfire missile is, what shock testing is. Then we'll highlight our project requirements and objectives, and then we'll discuss the engineering theory behind shock testing. After we're done with the background, we'll move on to the design development. We'll show how we broke down our system. We'll discuss how we use SolidWorks and MATLAB for analysis purposes, and then discuss how we compared materials for different fixture designs. And then after that, we'll have our conclusions and time for questions after that. So to introduce to you what a Hellfire missile is, it was first developed in 1971 by Lockheed Martin for the U.S. Army to use on Apache helicopters. Due to its tremendous battlefield success, the U.S. Navy adopted it in 1985 for shipboard use. This variant was called the B variant. It was the second one made. As of today, there's 18 total variants that have been developed. Each variant serves a specific purpose and functionality. An example of this is one missile might use heat-seeking guidance while another missile uses laser guidance. Whether the missile is mounted under a helicopter wing or stored on the deck of a naval ship, it's exposed to different environments and events. The environment that we're focused on for the purpose of this project is the missile being stored on the deck of a naval ship out at sea. And the event that we're focused on for this project is a shock event. Equipment that is qualified for shipboard use has to be designed to withstand extreme shock. Normally, this extreme shock is induced by an underwater explosion. This is originally done by taking the ship out to sea and detonating a test charge close to the ship. This can be costly and time-consuming because you have to supply the ship with a crew, and you have to take the ship out a safe distance away from the shore so that it's safe for everybody else. Also, the test serves a safety concern because you're using real explosives, and it can potentially cause bodily harm or cause harm to the naval ship. So the Navy, in order to alleviate these problems, developed shock testing machines in 1942. These shock testing machines allow testing to be done in a timelier manner and require less resources to do so. Also, they're safer because they don't use a real explosive in order to simulate that shock event. The Hellfire missile, due to its weight and size, qualifies for medium weight shock testing. Medium weight shock testing is defined as being able to test equipment between 550 pounds and 7,400 pounds. Here's a detailed sketch of what the medium weight shock testing machine is. In position 1, the hammer is raised to a specified height and then dropped and released and moves in a clockwise motion and impacts the anvil table, which induces a shock force to the anvil table and anything that is mounted on top of it. This is a simpler schematic of what the medium weight shock test machine is. To show a size comparison, here's Jordan at 6 foot tall, represented by a nice stick figure. The anvil table is 3 foot tall, so it goes about halfway up to his waist. And then any equipment that's being mounted on the medium weight shock testing machine is represented right here. For the purpose of this project, it's a Hellfire missile. Now that we've talked a little bit about the background of the project, I want to discuss the project requirements. The requirements that were given to us is that fixtures that are intended to simulate deck-mounted motions shall possess a resonant frequency between 12 and 16 hertz in the vertical direction. This is with the equipment installed on the fixture, so for the purpose of this project, it's the Hellfire missile. We chose to design for 14 hertz because it's in the middle of that range, and if we fell off short or a little high, we would still be within that range. The next requirement is that the total weight of the fixture, including the Hellfire missile, shall be below 7,400 pounds. If this weight limit is exceeded, the testing will have to be done in a different manner. It won't be able to be done on the medium weight shock test machine. The last requirement is that the fixture shall be constructed out of 316 stainless steel. This was a requirement that was given to us, but we chose to explore other options or other materials to see if there was potential for cost savings or weight savings. So after we were given those project requirements, we created some project objectives. The first objective was to design a test fixture. We chose to do this by modeling a lump mass model system in MATLAB. Once our findings from MATLAB, we use those to design the fixture and its components in a computer-aided drawing software. We chose SolidWorks for the computer-aided drawing software that we used. After we have the test fixture design, we compared our results based on the resonant frequency of the fixture weight, and manufacturing material cost. Next, Jordan will discuss with you a little bit behind the engineering degree.
So to go into a little bit of the engineering theory behind our system, first I'll go over some of the types of testing that can be performed to output a frequency response. I'll go over what a frequency response is and how to read a plot of a frequency response. And then I'll also go over how we model the system as a lump mass system with 4 degrees of freedom. That won't come until the design development section. So some of the types of testing are listed to the right. And for the first one, it requires a user input of a specific frequency. This can take multiple tests to analyze each frequency and the response of that system. The next is a chirp. It's not necessarily a test that can be performed, but rather an electronic signal that can be applied to a system that increases the frequency over time at a constant amplitude. This right here is an example of a chirp signal. As you can see in the top section, it's amplitude versus time, and the bottom is frequency versus time. Over time, as time increases, the frequency will increase as well, indicating that multiple frequencies can be tested. The drop test and the shock test are essentially the same test, in which they excite multiple frequencies, or essentially all frequencies, at an instant in time. For our purposes, we're going to be analyzing a shock test or a hammer test to indicate or simulate an ordnance from a detonation. So here is a frequency response. To find a frequency of a system, you find the natural frequency, or K, which is the stiffness of the material, and M, which is the mass of the material. So to find the natural frequency of a system, it's dependent upon the stiffness and the mass of the material. The peak right here in the Bode plot is known as the resonant frequency. The resonant frequency is different than the natural frequency and can be explained by the equation right here, where zeta is the damping ratio. For our case, zeta is so low that we can essentially consider the resonant frequency to be equivalent to the natural frequency.
For the design development of this project, for simplicity, we try to model the test fixture as a flat plate. But to reach our target frequency of 14 hertz, our weight was nearly 4 tons, which exceeds our weight limit, and is nearly 200 inches in length and 60 inches wide. As you can imagine, this would be very difficult to mount or remove. So this is why it started breaking up into multiple components. Here is a similar shock test for the Tomahawk missile. And as you can see, they have a mounting plate, a spacer, and a cradle with the missiles mounted on top, with the use of ratchet strings to chain the missile to the cradle, which we will also be doing. And that leads into our system breakdown of the missile container, the cradle, the spacer, mounting plate, and our bolted fasteners that we used. So here's the basic fixture concept, similar to what Drew showed before. So the hammer is going to swing through in a clockwise motion, strike the anvil, sending a shock through the test fixture to the missile. And as you can see, the components that are highlighted in red is what we will be designing.
So to go over what a lump mass system is, here we indicated that the anvil, the mounting plate, the spacer, and the cradle will all be lumped together as one mass. We can consider the missile to be rigidly attached to the structure or to the cradle as seen in the Tomahawk example. The 4 degrees of freedom are Y1, Y2, Y3, and Y4. So this is our frequency response of our system at the cradle. We achieved a 12 hertz frequency of the system, and we achieved this by creating or deriving the equations of motion of the system. We used MATLAB to model this system because we were able to quickly modify the mass and the stiffness of the material, which then allowed for us to go into SolidWorks and start creating the design.
So for the breakdown of the fixture, we modeled the missile container as the actual container itself, not just the missile, since this is how it would be transported on a naval vessel. As you can see, it's about 186 pounds and nearly 76 inches long, 14.5 inches wide. Here's the cradle that we made to house the missile for the testing machine. It weighs nearly 370 pounds. And to help conserve weight, we cut out sections. So here is the spacer, which is the heaviest component of the machine, and it weighs nearly 1,400 pounds. And this is what was actually used to tune the fixture itself. So increasing the width of the spacer increases the resonant frequency, whereas a narrow spacer will decrease the resonant frequency. And this was changed until we reached our target frequency of the 14 hertz. So here's just the mounting plate, as you can see. On the inside, this is where we'll mount the spacer, and on the outside is where it will clamp to the I-beams of the test machine. So for our bolts and fasteners that we'll be using, we're going to be using a 3/4 inch steel hex bolts to mount the fixture together for maintenance reasons. If something were to fatigue and break over time, they can be swapped out easily for different pieces. And also using clamps to attach the mounting plate to the I-beams. So for the SolidWorks analysis, we used a frequency study to find the natural frequencies of the system. Once I was able to change the geometry of the spacer to 14 hertz, I was able to input that into a linear dynamic study to simulate the impact of the hammer striking the system. So we use an acceleration shock spectrum that is generated by an actual Hornets test shown here. This isn't that same test, it's a very similar test, and as you can see, as our target at 14 hertz has a max of 130 Gs inputted into the system. And all acceleration shock spectrum is a graphical representation of the peak acceleration within a system or its potential to damage a structure. So from the SolidWorks analysis, you can see our displacement was very minimal. It was only 1/10 of an inch at the end of the cradle, whereas we had a max stress of 33 KSI. And that was found in the voltage connections between the spacer and the cradle. And as you can see that I put here as a side note, that the yield strength of the bolts are 50 KSI. So this will help ensure minimal damage between the fixtures.
So to go over the material comparison, although we were requested or specified to use 316 stainless steel, we opted to analyze 3 other materials. We chose, or we were required to use 316 stainless steel for its anti-corrosive properties. But when we looked at the other materials, we were looking for the fixture resonant frequency, the estimated cost, and the total weight of each of the materials. So with 316 stainless steel, we achieved a 14.721 natural frequency or resonant frequency of the system, and it cost to manufacture the fixture about $18,000. 304 stainless steel also has anti-corrosive properties, and still achieves a 14.887 resonant frequency and costs about $5,000 less.
So in conclusion, we showed you guys how we got to our final design. We used MATLAB and then took those findings and applied it to SolidWorks to further refine our design. Our design does meet all the requirements. It's made out of 316 stainless steel, and it's within the required frequency range of 12 to 16 hertz. Also, the total weight of the fixture is between 550 pounds and 7,400 pounds at 3,081 pounds. We would like to thank Mr. Cliff Holbrook, Mr. Jordan Dunn, Mr. Ryan Baker, Mr. Doug Sims, and Mr. Michael Jones from NSWC Crane for being great liaisons throughout this project. And we'd also like to thank Dr. Davis for being a great advisor throughout this project and all the other engineering faculty that helped us. So with that, here are our references, and we will open the floor up to questions.
Questions?
All right, really nice job, guys. Could you go back to your stress analysis for just a second? Yeah, there you go. So can you tell me how that was modeled? Those are constraints on, where are the constraints and where's the loading applied?
It's fixed all the way around at the bottom, as you can see with like the L shapes, and then the L shapes, and then It's kind of hard to see. You see the purple arrow down here. This is where the impact of the hammer will actually strike the system.
Okay, and you mentioned the yield strength of the bolts, so are the bolts actually part of this design, or?
Yeah, they're
are
part of it.
They're part of this analysis?
Yes.
And how did you model that as, just fixed to the units, or like the connection between the unit and the bolts?
In SolidWorks, they were just placed on top of each other. You don't really, I guess you don't
So is
really
that-
need the bolted connections in SolidWorks. It can be negligible, but we'll be using the 50 KSI field strength bolts to withstand that 33 KSI stress.
All right, okay, thanks.
It looks like the hammer is not in the scope of your project, but maybe you could answer this question anyway. How do they launch that thing?
So they use a overhead crane, and there are markings on the axle, I guess you would call it the axle, that shows how high you raise the hammer. The customers will either specify how high they want to raise it, or it'll be specified by a chart in one of our references that tells you how high to raise it based on the item weight.
Thanks.
Can you just re-explain how you got from your model of your degrees of freedom and that layout to the resonant frequencies of in the MATLAB earlier in the
Yeah.
presentation?
So what I did, I modeled it I found the equations of motion of the system. And then I did state space modeling to find where, here, I'll go back to the, so from this right here, I derived the equations of motion. And then from there, I use state space modeling, which allows for us to decrease a second order system to a first degree order and simplify the calculations to find the natural frequency of the system.
So each of the peak resonant frequencies essentially is each
Yes.
degree of freedom?
Yes, that's correct. This right here is at the cradle.
Yes, going back to the material that you were required to use, the 316 stainless steel, you also showed that the 314 was possible, that you could use it possible.
Yeah, every material that we tested we were able to achieve that, but looking at, kind of thinking about it more, like, we wouldn't want to use aluminum because of its fatigue life, and 304 stainless steel has some similar mechanical properties, but, and it also is cheaper, so that's maybe a more viable option. The Navy chooses to use 316 stainless steel just for consistency throughout their designs, and 4130 steel also works, but it doesn't have the corrosive properties that they prefer.
Thank you.
I've got kind of two questions, and I know the first one isn't really in the scope of your project, but can you speak to where the resonant frequency range comes from? Why is that important for something like this?
That resonant frequency range is actually from a military standard spec that we found that it's the range is derived from real world data that's been collected in similar events. And so I would imagine that it never really said how they came with that, but I would imagine it's just collected data and then an average range.
Because usually the test stand, you want to not have a resonant frequency in the areas that you might experience.
Can you repeat that?
It wasn't really a question. The second question was so you have your lumped model, and then you have the actual devices. Did you run the resonant tests again using SolidWorks?
Yes, that is correct.
Okay, because when you make the holes, what effect do those holes that you made in the spacer stand have on the frequency compared to the 1D model?
So for the MATLAB, it's a lumped mass, so it's all concentrated at one point. Whereas in SolidWorks, it's a distributed mass throughout the component itself. Does that answer your
So
question?
the holes can be deemed negligible for the purpose of SolidWorks. They don't really affect the analysis as much as one might think. It's from the source, from our people that we've talked to, engineers at Crane, they say it's generally like a 5% difference.
Okay.
So it's kind of negligible.
In the SolidWorks, they are fixed together.
Right, okay, thanks.
Any other questions?